Multiplicity of Euler phi function. The property states that phi of mn is equal to phi of m into phi of n whenever the GCD of m and n is equal to 1. Here m and n are any two positive integers. To find phi of mn, let us recall the definition of Euler phi function. We know that phi of mn is the number of non-negative integers less than mn and prime to mn. So by definition, phi of mn will be equal to number of j's in the range 0 to mn minus 1 which are relatively prime to mn. From this range 0, 1, 2, etc. mn minus 1, we will need to remove all those j's which are not relatively prime to mn. That is, we have to remove all those j's such that GCD of j and mn is greater than 1. Now for each j from our range, that is the set of integers 0, 1, 2, etc. mn minus 1, we let j1 be the least non-negative residue of j modulo m. That is, j1 will be the remainder obtained when we divide j by m. Then obviously 0 will be less than or equal to j1 and j1 will be less than m and j will be congruent to j1 modulo m. Similarly, we can assume that j2 is the least non-negative residue of j modulo n. Then 0 less than or equal to j2 less than n and j congruent to j2 modulo n. Thus, for each j in this range, we have obtained two integers j1 and j2 satisfying the system of congruence j congruent to j1 modulo m and j congruent to j2 modulo n. Now we can apply Chinese remainder theorem to the system of congruences j congruent to j1 modulo m, j congruent to j2 modulo n, since the moduli m and n are relatively prime. By Chinese remainder theorem, we know that this system will have a solution and it will have a unique solution j in the range 0 to mn minus 1. Since the set 0, 1, 2, etc. mn minus 1 is a complete system of residues, there will be exactly one solution to this system from this range. Now we know that j from our range will have no common factor with mn if and only if j has no common factor with m and j has no common factor with n. If not, suppose if j had some common factor, some non-trivial common factor with m, then that factor would be a common factor of j and mn as well. And this statement is equivalent to saying that j1 has no common factor with m and j2 has no common factor with n, since we have assumed that j is congruent to j1 modulo m and similarly j is congruent to j2 modulo n. So we have seen that whenever j satisfies this property, we will have two integers j1 and j2 satisfying these conditions. So we can say that there is a one-to-one correspondence between such j's and such ordered pairs j1, j2. Now, if we consider phi of mn, from the definition, this is equal to number of j's for which 0 less than or equal to j less than mn, and GCD of j and mn is equal to 1. And this can be expressed as the number of j1s which has no common factor with m into the number of j2s which have no common factor with n, using this one-to-one correspondence. And we can observe that the first number of such j1s is equal to phi of m from the definition of phi function. Similarly, this number of j2s for which 0 less than or equal to j2 less than n and j2 is relatively prime to n, this number is equal to phi of n as well. So, phi of mn is equal to phi of m into phi of n as required. So, whenever m and n are relatively prime, phi of mn is equal to phi of m into phi of n.